I'll do is let me just share with you the very general structure of this thing. Okay, this is a very big picture. So what you should see here is something that says course topics, and the course is called Strange and Beautiful Numbers. And basically the idea behind the course is we start with a real foundational number system and we just gradually build up complexity. So it'll start in places that you're probably familiar with, and then we're going to end up in some very, well, strange and beautiful places, really. So we begin with the integers, and that's going to be important for us, just because a lot of the material that we learn about in integers is going to be foundational for understanding these other kinds of numbers, okay? So if you think about it, you know, the integers basically are just the counting numbers and then their opposites, but it does not have any of the fractions and decimals in between. This is related to the idea of essentially number theory. So some of those who have either had a number theory course, perhaps with me or elsewhere, or who have studied number theory as like one of the topics that you've explored in this math studies circle, like the previous time we did it. Then a little bit of the material at the beginning of the course will probably be something that you've seen before, okay? So a few topics from that area will be things like modular arithmetic, because we'll need that a lot throughout the course. Let's say linear congruences, which is basically solving algebraic equations in modular arithmetic. The Euclidean algorithm is huge. I'll move this in just a second so you can see it better. So a lot of these things are going to be like really big pieces of what we end up doing. And you're going to need to have a pretty strong foundation in this area in order to be able to kind of move forward and understand some of these other kinds of numbers. But the idea is, you know, you have the number line, and as you go through, at least in the early part of the course, what we're going to be doing is sort of just gradually filling in the number line. So when you look at the integers, and I hope you can see what I'm kind of drawing now down here, the bottom near the screen, the bottom of the screen, the integers basically begin with the counting numbers. So 0, 1, 2, 3, etc., like this. And the opposites of those. So taking us into negative numbers. Okay, but it doesn't include any of the things in between. So we just basically have what we would call a discrete set of numbers on the number line. And it's amazing how much you can study just about these. I mean, you can make an entire career in mathematics just studying these numbers. There's still plenty that we don't know about them, believe it or not. But once we really get a solid foundation in that, and this is the part that may be probably familiar to a few of you already, but probably not most of you. Then we expand into the rational numbers. And what we do is something that mathematicians do a lot. You take some given mathematical structure that you've created, and you find a way to use it to sort of expand itself. They're called extensions often. And so we extend the integers into a larger number system called the rational numbers, which again, you learn about in school. It's essentially fractions, ratios of integers. But there are very specific ways that mathematicians do this that are really cool. For example, if you've studied group theory a little bit, you've learned that we can create new groups from old ones by using direct products, okay, which is essentially forming pairs or triples of elements from previously discovered groups. And that's essentially what we do with the rational numbers. We take integers and we pair them up, right? Think about it. When you have a fraction, you're making one number out of two numbers, right? You take a numerator and denominator and you somehow combine them into a single number. The same way that you do in groups, if you have two separate groups and you combine them into a single group with this direct product thing. And so that's what we're doing. We're building a new system called rational numbers using what we already have, the integers by putting them in pairs and then talking about how those pairs combine. So you have to talk about how do you add them, how do you multiply, how do you tell, like how do you know like the integers that you already have are actually already part of this system of rational numbers and work the same way. And that's essentially what you do. And for a good deal of human history, people thought that once you simply created these rational numbers, these fractions, then that would basically fill in all the rest of the number line. All the spaces in between would get covered by these fractions. Well, later on down the line, people discovered, and this is a long time ago, the Pythagoreans, for example, discovered that there are some numbers that are on the number line but cannot be described as rational numbers or ratios of integers. And then you begin talking about things like pi and the square root of 2 and things like that, that you simply can't describe as ratios of integers, as fractions. And so we discovered there's a whole other collection of numbers that belong on this number line that represent distances in some sense or lengths. And yet, the fractions just don't include those. And so then we extend out to the real number system, including the irrational numbers. And this is where, in order to do this, I mean, these are all topics that you've learned about in school so far, okay? But we're going to look at them in lots of different and deeper ways. So for example, when we do the rational numbers, I mean, we're just not going to talk about how you add, subtract, and multiply fractions, of course. There are lots of amazing, beautiful systems that help us look at rational numbers in brand new ways. One of those is called rational tangles, which we may not end up being able to get to just because we won't have enough time in the class. But it has to do with how you can kind of use these fractions or rational numbers to describe tangles or knots in ropes. Another one we'll look at is something called the Stern-Brokow tree, which is an amazing way of sort of organizing and categorizing the rational numbers that just generate some astonishingly beautiful and unexpected patterns. And it'll end up tying in with a lot of the things we learned about integers. Then we'll extend to the real numbers and irrational numbers. And when we do that, again, we're going to do it in some kind of different ways. We are going to build in some ideas from calculus. We'll talk a little bit about the idea. Well, let me type in a couple of these things so that you can look back at this later if you want to take a picture, okay? So with the rational numbers, we build them from the integers. That's the key thing. And then some other things you can look at are things called rational tangles. And you can also, there's something called the Stern-Brokow tree. Something else we might not get to, Fari sequences, all kinds of things like that. And let's see, I think I may have left out a letter, but I can't quite see here. Yes. There we go. And so we won't be able to probably do all of that, but quite honestly, that's one of my favorite parts of the course. There's such beautiful stuff in here. Then when we begin talking about irrational and real numbers, we'll do it. I mean, it's beautiful. You can talk about how can you make these weird numbers like pi and the golden ratio and this number you learn about in algebra later on called E. And all these other numbers, how can you build them together by starting with rational numbers? In other words, each time you're using the numbers you had before to do that. And it turns out, for those of you who are taking focusing on the sequences and series in this class, that's kind of how you do it. You sort of build real numbers from sequences of rational numbers. And so we'll talk about how you do that. And in the process, we're going to enter into some ideas from calculus. We'll end up talking about limits. We'll end up talking about something called Cauchy sequences, which are extremely important in building the real numbers. And it's going to be like how we can take sequences of numbers and use these to fill in the rest of a number line and make sure that we've actually included everything and that sort of thing. And then we're going to go on to okay, each time we're building new number systems, we're not creating brand new ones, we're just expanding them to include more numbers. So then we move on to the complex numbers, which some of you may have heard of as imaginary numbers involving this number I, the square root of -1. And we're going to do that primarily geometrically. Something that you don't learn about as much in school is the fact that complex numbers, not only do they solve new algebraic equations, they actually describe geometric transformations. And that's going to be our focus, just because it's a new way of looking at them that you don't usually learn about in school. So we're going to look at complex numbers from the perspective of geometric transformations primarily. So how can you use these numbers to do things like, how can you use them to rotate things? How can you use them to translate or slide things around, reflect things? And we'll talk a little bit, probably, if we have a chance, we'll talk a little bit about also how these, there's something kind of amazing about complex numbers. We'll talk about them a little bit from a calculus perspective. That will be a little bit beyond what we really have the ability to understand, but something about how they just, like, the real numbers feel incomplete. And it's like when you, basically it's a two-dimensional version of the real number system, okay? And by expanding it in this way, we sort of finish things off in ways that we realize, makes us realize that the real number system and the number line just doesn't quite have enough in it. So we'll look at these. Whether you've learned about complex numbers or not, we'll learn enough of that to kind of get us started, and then we'll kind of look at them in new ways that you don't usually talk about in school. And then we move on to the quaternions. We may not spend a lot of time with this, but this is sort of like, the real numbers are sort of one-dimensional because they fit on a line. The complex numbers are two-dimensional because they fit inside of a plane. You have a real axis and imaginary axis instead of an X and Y. Quaternions are a four-dimensional system, okay, which extends the complex number system. Okay, and we'll talk a little bit about that too, and they also have beautiful geometric interpretations. The fun thing about the quaternions is that while complex numbers can describe rotations and translations and reflections in two-dimensional space, quaternions can describe many of these same things in four-dimensional space. And so all of a sudden we're talking about higher dimensions. And so that's a really fun thing. Then probably my favorite part of all this that I'm looking forward to the most, and even if we have to not do quite as much with some of the earlier ones, we're going to try to talk about p-adic numbers. And what that does is going to be the first situation in which we're actually not expanding one thing after another. In order to get to the p-adic numbers, what we do is we kind of go back to the rational numbers and jump straight from there to the p-adic numbers and sort of skip the stuff in between. When I talked about the rational numbers before, I said we could kind of fill in the final remaining gaps in the number line by using sequences and series to create new numbers that fill in those missing spaces. Well, it turns out that if you start with the rational numbers, you can extend it in an entirely different way. And it's in a way that does not fill in the number line necessarily. It may fill in some of the gaps in the number line, but not all of them. But then at the same time that it does that, it also creates brand new numbers that really don't belong anywhere on the number line at all. And you do this by completely redefining the notion of distance. We have a very clear idea of distance on the number line. You look on the number line, and the farther apart they are on the number line, the greater the difference or distance between the two numbers. In the p-adic number systems, and by the way, there are an infinite number of them. There's one for every prime number. P is for prime. You completely redesign the idea of how large numbers are and how far apart they are from each other. Okay. So for example, a number like 2 to the 50th power is extremely small in this system. Okay. Whereas a number like 6 could be much larger. And you talk about how far, by redefining how far apart numbers are, you get really strange and interesting things. First of all, the numbers don't fit on a number line anymore. There is some kind of a distance relationship between them, but it's much more complex. Numbers don't fit in a nice, neat, continuous path with one larger than the next, larger than the next. They create a new topology in some sense, where they're grouped in order to describe the pictures that show you which numbers are close to each other, you end up creating a fractal, okay? And so it has sort of a fractal geometry or topology in these systems. And weirdly, you can represent it's a little harder to write the numbers down. It's a little harder to represent them, but when you do, you get digits, the digits, instead of perhaps like we know when we have decimals, the digits can go on forever to the right if we want to, because you can have recurring decimals like, 0.3 repeating is equal to 1/3. Well, with p-adic numbers, when you write them that way, because of the way we redefine distance, the numbers, the numerals, I should say, can go on forever to the left instead of to the right. And sort of after the decimal point, you can only have a finite, non-infinite number of places, but it can go on forever to the left instead. And then there are beautiful connections between how this looks in our number system versus the p-adic number system. And you can even do interesting things with these when it's not p-adic, when the number's not prime. You can still create systems, but they don't work quite as neatly as they do when you work with a prime number. So anyway, these are really amazing, very strange, very beautiful. And it takes a long time to get your head wrapped around them. They're very interesting things. And so we'll spend a fair amount of time on that. And then as time permits, we may also try to have a chance to talk about infinite numbers and the infinite number of infinite numbers and how you can have different sizes of infinity, how you measure those, different ways to construct them, things like that. So that tells you quite a bit about where we're going with it. We're not going to be able to do every single thing that I'd like to do. I believe it was a 14-week course. We have an hour and a half per session. We're going to go through the integer stuff pretty quickly because we'll only do the part of it that we really need to use in order to prepare us for the remainder of the topics. That's what it's going to look like. So it's just like how mathematics can create new and amazing systems that are not exactly what you always learn about in school. Does anyone have anything you'd like to ask or comment about that before we have Siddharth step in and do his presentation?